Welcome to AQA A-Level Physics, Measurements and the Errors, Limitations of Physical Measurements, Part 2. First off, we'll look at absolute uncertainty. We work out absolute uncertainty by dividing the resolution of the instrument by 2. Let's have an example of this. So we're measuring 37 degrees to the nearest degree Celsius. Now, the degree Celsius is the resolution, so we divide that by 2. So that means we have 37 plus or minus 0.5 degrees Celsius. We could also show this number from 37.5 and 36.5 being the upper and lower bounds. And if we do add 0.5 to this, we do get this. And if we take 0.5 from 37, we get 36.5. This is just another way of writing these bounds. And this here is the absolute uncertainty, 0.5. Say we're measuring something. Here is a ruler. And say these are the lengths of 2 lines, as they are in this case. This line measures 7mm and this line measures 12mm. Each of those lines are millimetres, meaning this ruler has a resolution of 1mm. So we can find the uncertainty by dividing the resolution by 2, so that's 0.5mm. Now we have uncertainty at every point we make a judgment. And we're making a judgment both here and here. Not just once with the thermometer. Because we have to judge where we start the line and where we end the line. Fill that in here. So how do we write that out with the absolute uncertainty if we have 2 uncertainties? Where we write 7mm and add the uncertainties together to get plus or minus 1mm. We could write that for the other line down here. And of course, this has an absolute uncertainty together of 1mm. Now, absolute uncertainty is good and all, but we can also use percentage uncertainty. And that's calculated by the absolute uncertainty over the value. So in this case, we would have the absolute uncertainty of 1 over the value of 7, which is about 14%. And we can do the same for the other line, which is about 8%. And we can write that out as 7mm plus or minus 14%, or 12mm plus or minus 8%. And that can tell us different things to the absolute uncertainty. But that's for one measurement. What if we have lots of different measurements? How do we find the percentage uncertainty of that? Well, say you have the values 52, 54, 51, 56, and 49. Let's find the percentage uncertainty. Now we find that with the equation half the range over the mean, and obviously times by 100 to get it as a percentage. The same goes for up here with timesing it by 100 to get a percentage. But you should be familiar with that by now. Now let's look at the range. Well, the range is 56 minus 49, which is 7, and 7 divided by 2 is 3.5. And if we look at the mean, well, the mean in this case would be 52.4. So we're looking at 3.5 over 52.4, which is about 7% if we times it by 100. So the percentage uncertainty for this lot of data is 7%, because we use the equation half range over the mean. We can also find percentage uncertainty from graphs. Let's draw an example graph out. and let's plot some random data points. Sure, you always use crosses or pluses when plotting data. Mine's a bit wonky, but I'm going to go with it. And here's the line of best fit, or one line of best fit. You should be familiar with the setup from GCSE. Now we could draw another line, which is about that. And we call that the worst acceptable line of best fit. There's values above and below, and it's roughly close to each of them. So it sort of does count as a line of best fit. It's just the worst one we could possibly draw. So we can work out the worst acceptable line of best fit from just data points. If, say, there was scattered more, it could be a much wider and further away from the line of best fit. We can also find the worst acceptable line of best fit by plotting these. Now these are error bars, and these are calculated from the absolute uncertainty. I'll show an example. Say 7 millimeters, plus or minus 1 millimeter. Say that's this data point here. Well, the actual value measured is 7, so you'll plot the x at 7. But plus 1 millimeter is 8, and minus 1 millimeter is 6, so it could be anywhere within there. So you plot 8 as the top and 6 at the bottom. So the value lies within there, but we actually measured the value at the x. And we can do that for all data points. And with these error bars, we can then draw a different worst acceptable line of best fit, but still going within all the error bars. Imagine this is within the error bar. I drew that a bit wonky. If we look at the gradient and intercept of this worst acceptable line of best fit for either of them, and at the gradient and y-intercept of the line of best fit, then we can find the percentage uncertainty of that data, much like we did here, but without the equation. We find the difference in the gradients and divide it by the gradient of the line of best fit. The same goes for the y-intercepts. And of course times by 100 to get percentage. That probably off the board a bit. But M1 I'm minus M2 over M1. Okay, now let's look at combining uncertainties. If we have A equals B plus C, and B and C both have uncertainties, how do we work out the uncertainty of A? Now we use the symbol delta to represent absolute uncertainty. So this sign here means the absolute uncertainty of A. And in this case, of the A equals B plus C, the absolute uncertainty of A is the absolute uncertainty of B plus the absolute uncertainty of C. That's wonky. If we look at this, this is the sign for percentage uncertainty, sigma. Percentage uncertainty of A equals percentage uncertainty of B plus percentage uncertainty of C. And this is true when A equals B times C. Because when it's timesing with percentage uncertainty, we add. If we have, say, A equals B over C, we still do this. Because we don't actually care about what the sign is, or what the operation is. We only care about adding all the terms involved with percentage. And lastly, if we have A equals B squared, that's percentage uncertainty of A equals percentage uncertainty of B times 2. Because this is just B add B, much like we saw here. Anyway, that concludes today's video on percentage uncertainties and absolute uncertainties. Hope you learned something. Goodbye.